Okay, howdy. This is the fourth of possibly 7 lectures on, or videos that comprise a single lecture on potentials and fields. So I've already looked at the potential and fields in 2 situations, and I want to have a more complicated task that's mainly for you. All right. So this is what that task looks like. So I've got these 4 different regions, and they each have electric fields in them. And I want you to go through and take these 8 points and rank which points have the largest and the smallest and the in-between magnitudes of the electric field. So these dashed lines are the equipotentials. Everywhere along this dashed line you have the same potential. All right, they're marked either every 1 or every 2nd or every 3rd. One of these is marked. I guess every 4th here is marked. And they tell you the values of the potential. In your eCampus thing, you've already got a copy of this, so you should work this out before you watch this video, right? So if you haven't already, pause this and work it out and talk with people and all those other fun things that you have to do before you listen to what I'm going to say. But really, this is just a ranking task, so go ahead, rank these, figure out how to rank these, rank them, explain why. You always have to explain why, because if you explain why, then if there's an issue, then it's easier for you to tell why you have an issue with that. And then tell me how sure you are with your reasoning. All right, and I've got 5 qualitative things down here. Those are actually going to change soon. I think we need to be less sure and more doubtful. All right, so go ahead, pause. When you come back, we'll go ahead and do whatever's next. All right. So how am I going to think about this? Well, the first thing that I'm probably going to think about is what am I going to use to figure this out? What have we been using in the past 2 examples, right? We've been using this this equation that's only true for uniform fields, right? That the potential difference is equal to minus that uniform field times the distance between them. And in this case, we do have uniform fields. If you look at these equipotentials, you'll see that these are all uniformly spaced, which means the fields are going to be uniform. On top of that, you'll also notice that each one of these 4 distances is 20 centimeters. It says that it's always 20 centimeters in the problem description as well, but it definitely is when you look at what I've put down here. So having those 4 things all be the same means that all you have to do is figure out what the slope is at any particular point along here. And we also have a very useful thing here, which is that since these are all equally spaced equipotentials, right? Since there's no difference in between them, that means that for each one of these 4 regions, the 2 points have the same value of delta V, and so instead of trying to figure out what the distances are between here, right, what we can do is we can just figure out for each region what the electric field is, and then each one of those pairs is going to have the same issue. All right, and if we just need to figure out for that region, well, we really just have to find delta V from the rightmost to the leftmost and divide by 20. All right, so here it's 110 volts minus 30 volts. That's, I don't know, 80 volts divided by 20. That's 4 volts per centimeter, which would be, I guess, 400 volts per meter if we're using the SI unit. But we don't even have to go through the worry of calculating an actual E. We don't have to figure out what the electric field is. Because the distances are all the same, we just have to look at what the difference between these 2 points are, and whatever that difference is going to be proportional to the field, right? So that's all we really have to do in this case. So if I'm looking at like A and B, that's 80 volts. C and D, that's 60 volts. E and F, that's 0 minus 30, that's 30 volts. G and H, 960 minus 900, that's 60 volts. So it's just that difference that's important, right? This absolute value doesn't matter. That doesn't do anything to the field, right? That's just a number, right? The only thing we care about is the slope, or the only thing we care about is the change, right? How much the potential is changing is how much force we have, or how much field we have, and therefore how much force we're going to have if we put a charged particle in that point, okay? So, so now we've got all of these things, and we just have to rank with these delta V's. Well, A and B have the largest delta V, right, which is 80 volts over the 20 centimeters. So those guys are going to be the greatest. A and B are going to be the greatest, right? C and D have 60 volts. So does G and H. So C, D, G, H, those are all equal, so we can write them down in any order we want right here. So as long as you have those four in the middle there, you are fine. Okay, and then E and F have the weakest field there with the delta V is 30, and there you are at the end. Okay, so that's all we really were looking for in this case, right? So this is what we know about halfway through the lecture, right? We know that at all points in space there's this electric potential. This potential is related to the potential energy by the charge on an object. So the potential energy on an object, the electric potential energy on the object is equal to the charge of the object times the electric potential at that point. That electric potential is the sum of all the contributions of all the other charged particles in the universe, or in the problem, and usually in the problem is better, because in that case it'll be 1 or 2 rather than 10 million. And so you just multiply that number, and that's all you need. That's it. Okay. The electric field, if the electric field is uniform, then delta V is just the difference between the potential at 2 points is just the separation between those points, as long as you're along the same direction as E, right? As if there's some displacement, right? If E is up and 1 point is to your left and 1 point is directly in the center, then it's only how far up you have to go. But that's a complication that I'm not really going to worry about, because I don't think it's very interesting for this particular level of a class. It's very important, but I think it's more confusing than important. So that's it. We've got this potential. It turns into a potential energy, or we can use it as a field, either way, and then we can do our magic with it, right? All that physics magic that everybody loves. Okay. So I will talk to you in just a moment while this renders, and then we can go on to the next part, all right? See you around.